So what we're doing today is we're continuing on with these properties of rational, or these, not rational, these radical expressions, and simplifying these radical expressions. Now this here isn't in your notes because it's not explicitly written, but these are the simplest forms that we had yesterday. Because we looked at these yesterday. If it's in simplest form, no radicands have perfect nth powers as factors other than 1. No radicands contain fractions, and no radicals appear in the denominator of fraction. And these here are kind of guidelines so that we know that it's in simplest form. Now, some of the assignments that we have isn't necessarily keeping this first one here true, because 7 to the 5/4 would be accepted. It's not technically in simplest radical form, but it's more in exponential form, so it kind of works. It's a little bit of a loophole. So what we're looking at today is some other properties here. So these two here. Now the product property says that I can take two things, be multiplied inside the root, and split them apart. Now I can go the other direction as long as they have the same root. So the square root of 2 times the square root of 2, I can put it as a square root of 2 times 2. We can put them back together, or we can split them apart. Because sometimes it's going to be easier to have them together, or it could be easier to have them apart, depending on what they are. The same thing is true with our division. If we have something being divided inside a radical, we can split them apart so that we have the radicals on top and bottom. So let's look at these here. So the first one we're going to look at is the cubed root of 12 times the cubed root of 18. So if we have something inside these radicals to the third power times itself 3 times, then the radical would reduce. So what we can do is we can do the prime factorization, or our factor trees, to see how these break down. Because if I do have cubes, perfect cubes, then we can simplify it. Well, 12, let's just start off with 2, would be 2 times what? 6. 6 will reduce to 2 times 3. And I'm just rewriting this here so we can see what the factors of 12 are. So we know that we have 2 squared times 3 is the prime factorization. These here. So I could rewrite the cubed root of 12 as 2 squared times 3. Because again, we want to rewrite this so I can see the perfect cubes, or the perfect nth roots, so they'll match up. And here we're looking for cubes. Any questions on this here so far? Okay, I'm going to erase this here, because the next one we need to look at is for 18, because we need to break it down. So what number do we know would multiply into 18? Smallest prime. 2 times 9. Because 2 works out nicely. It is a prime number. Now 9 is what? 3 and 3. So our prime factorization for this here would be 2 times 3 squared. So we just really broken these numbers down so they're a little bit easier to work with. Now again, our first property says as long as the roots are the same, we both have cubed roots, we can multiply what's inside the roots. So I have 2 squared times 2, which would be what? 2 squared times 2 would be 2 to the third, because how many do I have? I have 3 of them. We have 3 times 3 squared, well that'd be times 3 to the third. So we multiplied these together, we got 2 to the third times 3 to the third, because we have 3 in both spots. Now we could see that the cubed root and the third powers would simplify here. But if we want to get a little bit technical on how we would write this, is we can move that cubed to the outside. Because we looked at this yesterday, our power of a product tells us that we can do this. And now it's a little bit easier to see that these here would cancel, leaving us with 2 times 3. And 2 times 3 is 6. And we've got our answer here. Yeah, go on and try it. Let's try that. Try typing this into the calculator. Cube root of 12 times cube root of 18. Let's see what we get. Yeah. If you don't have a calculator, grab the yellow ones. The TI-30XS. They work quite nicely too. Yep. Now, if we plug this into the calculator, what did it give you? 6. So it worked out. Let's look at the other one here. The 4th root of 80 over the 4th root of 5. Now, we can plug this in the calculator and we can see if it gives us an answer. And it does. It tells us it's 2. Now, let's go about seeing how this works. Now, our division property we just saw a minute ago lets us take these 2 roots because they're both the 4th root, and we can put them together because the 4th root of 80 divided by the 4th root of 5 is going to be the same as the 4th root of 80 divided by 5. These are going to be the same. Now, 80 divided by 5 is 16. So it makes it a little bit easier to work with because we can do that division to simplify it down.
So I was getting asked on the last question. Couldn't we have just done 12 times 18, just like we just did 80 divided by 5?
Yes.
That would have gave us, I think it was 216.
And
then you could have just plugged it in like that.
Yep, 216 is the same as 6 cubed. Right, if we can see that the perfect cubes and see how they work, we can pull them out. Because if you can find those, we can pull them out, and it's easier to work with. But sometimes it's not as easy to see what all the perfect cubes are, especially our 4th degrees. Now here, 16 is 2 to the 4th, which would give us 2. So it worked out here. All right, let's go to the next one. The cubed root of 4 times the cubed root of 128. We'll go on and plug that in, see if it gives us a nice answer. And it does, doesn't it? So it works out that these here, some of these here, we can plug them in. If it gives us a nice answer, then we're done. How about the next one? The 5th root of 192 over the 5th root of 6. I feel like this, no, it's not 2. No, it's 2, okay. So it works out nicely because if we get these whole number answers, the calculator is going to be able to solve them if it reduces down like this here. And that's kind of nice. Makes these easier to work. All right, let's do it again. The cubed root of 135. Because if it gives us that nice answer, we're done. This is easy to do. What does it give us? 5.1. So it's giving us a non-repeating, non-terminating decimal point. Okay. So let's look at this here. We're going to look at this one here. We'll skip this next one, and we'll come back to it in a minute. So what we have to do here is we need to find the perfect cubes. because that non-repeating, non-terminating decimal tells me that this will not fully simplify. Because like all the ones that we've had previously, we were able to pull everything out. All the radicals simplified out completely. So what that means here is that something's not going to simplify out completely. So when we look at 135, let's look at the factors. So what's a number that we know for sure will go into 135? Or a prime number? 5. Let's start with 5. It'd be 5 times 2, 27. 27 seems interesting. What prime numbers go into 27? So 3 times 9. And 9 is 3 times 3. So we have 3 times 3 times 3 times 5. Or we can say 3 cubed times 5 would give us 135. Well, with our properties we have today, so we can split this up in the cubed root of 3 to the third times the cubed root of 5. Well, the cubed root of 3 to the third is just going to be 3, and then we have the cubed root of 5. And that's it there. That's why this calculator, neither one, will give us what it is with radicals. Because the cubed root of 5 is a non-repeating, non-terminating decimal, and even the TI-30XS doesn't like doing that. It doesn't like those. So that's our answer. That's what we have for this here. Any questions on this here? Are you ready for the next one? Yes? Okay. We're skipping over to this one here. I want to do the two divisions together because I looked at that this morning and I didn't want to jump from the multiplication, the individual one to the division to the individual to the division. I want to do this one here. The cubed root of 500 is what we're going to be looking at. Yeah, stay. And I have a feeling it gives us another non-repeating, non-terminating decimal. So we need to work this out. So when we look at 500, again, we're going to look at prime factors. So what one do we know for sure? 5 times 100, yes. 100 is factorable. We can use 10 and 10. 10 works just fine, which will give us 2 and 5, 2 and 5. And those are all the way broken down. Now, if we look at this here, we have two different numbers. We have 5 once, 2, 3 times. 5 to the third.
So you already know that that 5 is going to be out, since there's 3 of them, can you already take it out?
Right.
And just essentially put there.
Yes. So 5 to the third, we know that's going to come out. Yes, because we know 5 to the third, and that third root would simplify, so we move the 5 outside. Now, this is getting more into number theory on how we write this, what's inside the parenthesis, or inside the radical, is we don't normally want to leave it as 2 squared. Because 2 squared is what? 4. We're just going to leave it as 4. Because if we can simplify something as a power, because 2 squared simplifies to 4, that's fine. A number to a power, if it simplifies, we'll simplify it. Now, 7 to the 5/4. Now, like we saw yesterday, 7 to the 5/4, well, that does not simplify nicely. Because we could have it, rewrite it, if we have it in radical form, as the 4th root of 7 to the 5th. Then, if we actually have it as this here, then we would want to put the 7, actually find out what 7 to the 5th is. Then we would do it that way. But 7 to the 5/4, we'll leave it as this here. Because it's not inside of a radical, we don't have it, it's not as complex. Any questions on any of this here so far? Are you good with this here? Yes? Okay, let's come back over to this here. The 5th root of 7 divided by the 5th root of 8. Now, the reason we need to simplify this here is because we cannot have a radical in the denominator. We cannot have the 5th root of 8 in the denominator. And the best reasoning for this, that the reason we can't leave it in this form, is because we don't want a non-repeating, non-terminating decimal in the denominator, the bottom of the fraction. That's about it. So what we want to do is we want to be able to get rid of this radical in the denominator. Okay. I want to move you over here. We're going to look at 2 ways to do this. One of these is going to add another step or 2. And one of them is going to be a little bit easier. Well, 7's prime, we're not going to deal anything with that. Can I rewrite 8 with using its factors? Well, what are the factors of 8? Well, it's 2 times 4, and 4 is what? 2 times 2, yes? 8 is 2 to the 3rd power. Are we good with saying that there? So I can come down here and say 2 to the 3rd, okay? So we started out with the 5th root of 7 over the 5th root of 8, and we kind of rewrote 8 as 2 to the 3rd power. Now, really, in the denominator, if I had 2 to what power would be nice? Because if I didn't have that 3, what would be a better number to have than 3? 5, because if I had 2 to the 5th, well, the 5th root and 5 would cancel out, yes? Okay. So what could I multiply 2 to the 3rd by to get it to be 2 to the 5th? And we would take the 5th root, because as long as the roots are the same, we can multiply what's inside. Well, 2 to the 3rd times 2 squared would give me 2 to the 5th, yes? But we have to multiply it on top and bottom. Because really, what is this here? 1. Anything divided by itself is 1. So really, we're just multiplying this rational expression, this fraction, by 1. We're just multiplying it by 1. That's why we can do this and nothing changes. Now in the denominator, move that up just a little bit, we'll have the 5th root of 2 to the 5th, because 2 to the 3rd times 2 squared would give me 2 to the 5th power. In the numerator, we're going to have 7 times 2 squared. The 5th root is 7 times 2 squared. Well, here the 5th root and 5 will cancel out, leaving us with 2. Now let's look at the numerator. Okay, I'm going to pause there for a second. So any questions on how we got the denominator to be 2? Okay, the numerator. So we have 7 and 2 squared inside this radical, yes? Can we factor 7? No, it's prime, yes? So 1 and 7, that's as far as it goes. So there's no way that I can take the 5th root of 2 squared or the 5th root of 7 or any combination of these two numbers. Right? That's as simplified as it gets, yes? So let's just multiply them together. Well, I'll pull this up here. Because 2 squared is what? 7 times 4 is? So this here in simplified form is the 5th root of 28 divided by 2. And that's it. That's all we have to do for this here. Questions on this here? Okay. I said there's another way we can do this, yes? Okay. Yeah, I mean, I agree with that. Okay. Come here. Go away. There is another way that we can do this here. Come on. There you go. I would not advise this method because it's going to make you reduce at the end. Now we said if I have a number to the 5th power and radical would reduce, yes? Well, in the denominator I have 8, yes? Okay. That would work, wouldn't it? Because the denominator 8 times 8 to the 4th is 8 to the 5th power, yes? So in the denominator, we'd have the 5th root of 8 to the 5th. In the numerator, we'd have the 5th root of 7 times 8 to the 4th. Well, these would simplify to, not 2, but we would have 8, yes? Wait a minute. Up here, I do have the 5th root of 7 times, well, 2 is 2 to the 3rd, yes? Now it's to the 4th, so we really have 2 to the 12th power. I'm going to break this up just so that it's going to make sense. Because really, what did I do? 2 to the 10th, just 2 to the 10th plus 2. Well, I have 2 extra 2's in the numerator, because 5 divided by 2 is, I'll write this out, so we're not just talking through it. So we look at this here. Okay, come on. We can really break this up into the 5th root of 2 to the 10th times the 5th root of 7 times 2 squared over 8. Because this here actually reduces to 2 squared times the 5th root of 28 over 8. We get extra factors. Because we have an extra set of 4 that we had to pull out, or essentially 16, that we had to pull out of the numerator. Oh, it's not even 16. Because 2 times 2 is, because 4 is 16, so 32, 60, 32 squared. Extra factors in the numerator that we had to get out, we have to pull out. Does that make sense? So it does work, but especially in big ideas, it's going to mark it wrong because this is not in simplest form, because we'd have to reduce that. So whenever we do these here, if we can find out what's going to make the denominator in simplest form, we need to do that. We don't need extra factors. I'm going to tell you right now that does not, the calculator will not do this here. It's not going to do it. It's going to throw it back out. Now 4, how can we rewrite 4? 2 squared. we'll need our fourth roots because there's the only way we can multiply on top and bottom is with fourth roots. We need the roots to be the same. Well, how many 2's do I need to get those radicals to reduce? 4, right? Because it's the fourth root. How many do I have? 2. How many more do I need? So we need to multiply top and bottom by 2 squared. Well, the denominator is going to become, well, 2. You can rewrite it as the fourth root of 2 to the fourth. That's nothing wrong with that. But what do we know is going to happen? We should get 2 to the fourth, which is going to simplify to 2. Yes, that's our goal. That's why we're doing this. So we know it's going to be 2. Is 19 prime? Well, 2 won't divide into it, will it? Well, 3? No, because 1 plus 9 is 10. 4 doesn't go into it. 5, okay, well, that's prime, yes? And the reason I point that out is because the only way that we will get something to come out of the numerators is if there are like factors in both. Because if 19 had 2 squared as a factor, as one of its factors, and with the other 2 squared, that would give me 4 2's, yes? Then it would reduce. Well, since I know 19 is prime, 2 squared is not going to reduce. Whatever we're going to have here will not reduce either. So we're going to have 19 times 4, because 2 squared is 4. And then we just need to multiply these here. Because 4 times 9 is 36, so we drop the 6, carry the 3. 4 times 1 is 4, plus 3 is 7. Or we could have plugged that in the calculator, 4 times 19. Oh, didn't mean to do that. So any questions on this here? This kind of makes sense how we're manipulating these numbers. Yes? Okay. Now we want to write this in simplest form. And I believe these are the last type that we're going to look at, because I think that pretty much rounds out the notes. Yes? Okay. Again, we cannot have square roots in the denominator. We cannot have radicals in the denominator. So we're going to use our irrational conjugates. And what that means is we're going to multiply this by 5 minus the square root of 3. We change the sign in front of the radical, and we're going to multiply it. So we're just changing the sign in front of the radical. And we'll see this here, because this works specifically for this reason. Now, the numerator is just going to be 5 minus the square root of 3, because we're multiplying it by 1. Because 5 minus square root of 3 times 1 is just 5 minus square root of 3. That's the nice thing about 1. Now, the denominator we're going to multiply through. Well, 5 times 5 would give us 25. 5 times negative square root of 3 would be minus 5 square root of 3. Square root of 3 times 5 is going to be plus 5 square root of 3. And square root of 3 times negative square root of 3 is going to be negative square root of 9. We could have said minus the square root of 3 squared. There's different ways we could have written that. Well, you're probably looking at this thinking, well, we did that to get rid of square roots. Well, we just went from 1 square root to 3, didn't we? Well, let's see what happens, because there's something that's going to happen with this here. In the numerator, we still have 5 minus square root of 3. The denominator, we have 25. Well, like terms here, what is negative 5 square root of 3 plus 5 square root of 3? So what happens to these middle two? They become 0. Negative 5 plus 5 is 0, yes? They're gone. Minus. What's the square root of 9? So multiplying by its conjugate got rid of every square root. This is what we did with I. A plus bi times a minus bi got rid of all the I terms. We're almost done. 25 minus 3 is 22. Any questions on this here? We're good with this here? You beat me to that answer? Yep. It just has these flipped? Yeah. I mean, that's the same thing, isn't it? Negative square root of 3 plus 5 is the same as 5 minus square root of 3. So what can we do? How did y'all get that? Type it in. Type this in. See what you get. Yes. What did you all get? Over 5, 2, 3. Yep. The TI-84 graphing calculators do not simplify in radical form. The TI-30XS does. That's why we like having both. That's why I say on the ACT, have both if you need it. Because doing this by hand is fine, but unless you are proficient in doing these and have done these and are kind of used to knowing what to do, trying to work this out by hand compared to plugging it into the yellow calculator isn't going to help you. I mean, if you can plug it in and get the answer like that, do that, especially on the ACT where time matters. Type it in. Because if we were doing this, we would multiply top and bottom by square root of 7 plus 2 to simplify down. Try this one. 5 divided by negative 5 minus 3 square root of 3. I'll try it on this here. What did it give you? You're welcome. So even though the graphing calculator can do so much more than the TI-30XS, this one here has things it can do better. Are there ways to use the graphing calculator to get to this? Well, yes, but they're going to be more complex than what they're worth. Any questions on these here? Let's try this one here, because this one looks like it might give us some issues.
Negative 20 square root 3 minus 4 square root 2 for 73.
Give it to us. Will it always give you the answer? Well, no. Because if the numbers get too big, like we know with square roots, because the TI-30X will work with most square roots, it'll simplify it, leave it in simplest form. but if the numbers get too big, it's going to turn it into decimals. So there's a limit to the memory space that it has.